All right. Thank you very much, Alex, for the brief introduction. Yeah, so quite late already, but let's see how many will join the session. So the idea of this whole thing is actually to showcase a little bit what we built in a private project. Usually, as it is, private projects, they spark joy, and usually it's a quite nice idea to get your hands dirty on a little bit of tech. All right, then maybe jump in a few sentences about us. So my name is Kevin Gomez. Like Alex said, I am part of Neo4j. I joined Neo4j 3 years ago as a professional services consultant. And I was part and was involved in many, many different areas of projects, from customers, from, I don't know, from finance or medicine to automobile and so on. So I have seen a lot of solutions, a lot of projects, a lot of use cases, and almost all of them had the same problem. And this project that we showcase here is at least one step ahead to maybe come to a solution to help all of those customers, actually. And with me, there's Christopher Rost, and maybe Christopher, you can introduce yourself.
Yeah, thanks, Kevin. Yeah, also warm welcome from my side. Yeah, I'm, as I said, Christopher from Leipzig University, and I have done my PhD in with the topics of temporal graphs and graph streams. And therefore, yeah, so we are friends of each other, and we think, or we thought that's a good way to share our experiences in that field and to present you, yeah, like said, like an open source project that we developed on. So,
yeah. All right, then I think we can go ahead. So what to expect from this talk? We will showcase you our little demo in the end of the talk, but we will cover basically those 4 aspects here. We will talk about basics and some ground basics around graph stream general. What is CDC, Change Data Capture in Neo4j? And then we will go into more detail when it comes down to grouping graph streams and why we should group and analyze CDC graph streams. Actually quite interesting. Okay, Christopher, please jump into.
Yeah, so I will start with what a graph stream is in our terms. So a graph stream in general, also called a streaming graph in literature, is more or less just an event stream, so stream of events, where an event can be like a graph element itself or a graph update. And graph element could be like just a plain vertex, it could be an edge, it could be a triple. Yeah, and these elements could be labeled if we are on the property in the property graph domain. They can be attributed and they can be timestamped. On the other hand, if we talk about a graph stream as graph updates, that could be modifications of the graph. For example, like the addition of an edge, the deletion of a vertex, the addition of a property to a vertex, the deletion of a property of an edge, for example. Yeah, here on the bottom you see an example graph stream where the events are triples, so we have vertices of different label, here colorized, and edges that coming continuously over time in our stream. So the benefits of seeing a graph in the streaming model, I think it's quite clear. So we can not just having like a one-time query execution, but we can execute queries and graph analyses for sure as well, concurrently with the graph elements that arrive or with the graph updates. And then we get these updates of the analysis results with a low latency in near real time. So we don't have to wait or execute them like once a day. We get them by real time. And the goal can be like for monitoring purposes to just, I don't know, watch my use case, or to get like a notification when something is above, I don't know, a threshold or whatever. And for sure, like a reactivity to react on the changes that happen. So now I hand over again to Kevin, and he explains what CDC is.
Yes, thank you very much. All right, so CDC, short for Change Data Capture. It's a feature that a lot of database systems include, as well as Neo4j, of course. CDC in a nutshell is information about what changes in your graph or what changes in your database. This is in a nutshell, right? So imagine you have this piece of information available. Then you are able to tackle those three aspects that we see here in front of us. First, we can react to events. We can say, hey, I want to detect and respond to change in our data. The second one is auditing, meaning I want to actually very specifically know the before and the after state of the changes that occurred in our database. And I also want to have some meta information about who did the change and what changed. And last but not least, also replication is a very common use case among our customers, for example, where they want to use CDC to create a copy of their maybe in production database to have a copy available maybe for development, maybe for testing or whatsoever, right? So all those three aspects, they can be tackled when CDC is in place. By the way, those slides, they are based on a CDC talk of Stu Moore from Notes 2023. So if you want to have way more in-depth information about CDC, then feel free to go a year back and then rewatch this. All right. Okay, so how are changes currently captured inside Neo4j? Yeah, so first, step one, we need graph changes. Yeah, so we need a live graph, something happens inside the graph. The second one is, and it is how it is implemented right now, we enrich the transaction log. So there's a transaction log available in Neo4j that holds a ton of information around transactions, like when transaction started, when it was committed, which user was it, how he was connected, which role he had, and so on and so on. So we already capture quite a lot of information. And with the CDC feature, we enrich this further. So we add more information to the transaction log, right? So this is the step two, we enrich the transaction log. And step three is we provide a set of functions to be able to actually read the transaction log and to query the transaction log, so the CDC content of the transaction log, right? And this is, state-of-the-art implementation. I think I saw it everywhere on classical relational database management systems. CDC was always incorporated within transaction log. All right, next slide, please. Okay, so when you want to activate the CDC feature within your Neo4j instance, then you are able to set the specific option here. So set option, transaction log enrichment, and then to a mode. The default one is off. So by default, it's not on. Reason for that is when we enrich the transaction log, it will become bigger, of course, right? And you have to think about how long do you want to store this data? How long do you want to save your transaction log and your change data? So by default, it's off. But if you want to enable it, then you have the option between div and full. By the way, I will give you an example how this looks like in a couple of minutes, but for now, let me just explain you the difference between div and full. It's very easy, to be honest. For example, imagine you have a node in your database, a person node, and this name of the person is Kevin Gomez. Let's say you have the div mode, and now you rename, you update this specific node from Kevin Gomez to Christopher Rost. Then in the div mode, you will have a JSON extract, and only the difference of those properties, meaning the property, the name property, only this change will be contained in the change data capture. When you have compared to that the full mode, that means that not only the property that changed will be displayed in the change data capture, but all other properties as well. So maybe my height, maybe my salary, whatsoever, right? So all properties that are assigned to the specific node will then be displayed in the change data capture when you have the full mode. All right? Okay, next one, please. There we go. Okay, so those are the functions that we currently have available querying the CDC, which is very simple, to be honest. We have the earliest, which will provide us with a change ID of the earliest available change. Changes are always bound to transactions, right? So this is the earliest available from the moment you start or you enable the option. Then we have current, which is the last committed transaction and the last ID of this event. And then we have query. And then query, basically, you can put in an ID, change ID, and then you get all the CDC back from that ID on. So from that on, right? And not only the specific transaction, but basically all that comes afterwards. So we have these functions in place. All right, next one. So this is an example for CDC. So we have a change event. Change events have IDs here on this example. And like I said, they are bound usually to transaction IDs. and even more. Like the next page, you will see metadata. And here you can see already quite a lot of meta information, like start time of the transaction, the commit time. We have the timestamps, of course. We have the authenticated user. We have the executing user. Also interesting, so that covers impersonation and that area. You see the connection type, the protocol that was used, even the IPs. And we see in the bottom the capture mode. This is regarded as diff. And then to the actual event itself, you can see the event was executed on a specific element ID, that is a node or relationship ID inside the database. The event type in this scenario is N. That means something occurred on a node. It would be R if something occurred on a relationship. Then we have the operation. In this scenario, it's C. That means something was created. And then you will get the payload information of the specific node here. So a person node was created, and you can see in the state we have after and before. And after, that means after the change, now we have a person node and the name is Christopher Rost. And before it was null, of course, since the node was created, right? Okay, so much to that. Next one, please. So here we are now. We have now our Neo4j database in the middle, and the change data capture is enabled, and the transaction log is enriched. Now, in our scenario, we want to make use of that. And please, next slide. Now we want to make use of Kafka. I'm pretty sure almost all of you will know Kafka. Kafka is we will use it as a stream component in this scenario. And there's something very handy available around Neo4j, and that is a connector. We have a lot of connectors available, but here for this use case, we want to use the CDC Kafka connector. And that one enables us to directly read information from the enriched transaction log and push it to our Kafka topic. Yeah. And in the next slide, you will see an example how the CDC Kafka connector is configured. And yeah, as a caveat, we can configure this connector in both ways. We can configure it as a sink or as a source. In this scenario, we want to read from Neo4j and then push it into Kafka. Yeah, so we configure it as a Neo4j sink connector. Yeah, here in this scenario with Avro is the serializer that is in use. We say those two topics, we can see station and trips. So that means we create two topics where we push the CDC data into. And then we have a lot, a bit of meta information and configuration. So the URI further on the bottom, we see the Neo4j username, we see the password. And then something quite interesting, and it's also quite new. I believe it's in Neo4j since 5.20, if I'm not wrong. So please correct me if I'm wrong, guys. We have the option to define patterns. And this is super interesting because with patterns, we can do something like a filter on our CDC content. So on our CDC will capture all changes that occur in the database, right? But with the pattern that we can define here, we can say, hey, I'm only interested on station nodes maybe, or on person nodes or whatsoever. We can say, I'm only interested on those specific nodes and all the change data that occurred across those nodes. Yeah, in the scenario here, we define two patterns, one that looks on station nodes in this scenario, and the other one looks on trip information. And the trip information is a relationship that occurs between two stations, so start station and an end station. Yeah, and you can define many more patterns. It's quite powerful, and it's very easy to use. So feel free to get your hands on this example as well. All right, further in the topics, why grouping graph streams? Christopher.
Yeah, that's right. So now we heard, okay, what a graph stream is and what a CDC is. And now I will just explain you in general why grouping a graph stream can be a good choice of an analytics of graph streams. So what is grouping a graph stream? So imagine here in our example, we have a graph stream on the top left side. So we have nodes of different labels, which are here the colors, and the edges of different labels. So when we group it, we first define a window, for the most recent time unit that we want to capture, for example, 10 minutes or 15 minutes or 10 seconds. And then the algorithm groups this graph by characteristics that we can define. Here in this example, it's just a label. That means all nodes with the same label are grouped together and all edges with the same label are grouped together. And the result here is again a graph stream that is continuously produced in this grouping. And while the window changes in our stream, so new edges go or new elements go in the window, some of them go out, then the grouping result updates and we get a new grouping of this graph. So this is the main idea behind the grouping. So why grouping a graph stream is useful? Sure, graph streams may be heterogeneous. So imagine we're having hundreds and hundreds of labels in our graph, and they arrive at a high frequency. So it is powerful for the exploration and to reduce the complexity of our graph stream in general. So the good thing is that with the grouping, we can summarize these graph elements or also graph updates on similar characteristics. And these characteristics could be like the time, so they happened at a specific time, which we cover by the windowing. Could be like the structure, so the same, so edges that are connected to the same vertices. And it can be the content, so for example, the label or values of the properties in the graph elements. And in our grouping, we realized that by so-called grouping key functions, and these functions map the graph element, for example, a vertex or an edge, to a specific grouping key. And that could be everything that is part of the payload of a vertex or an edge. This could be, like I said, a property value, or we define our own user-defined functions that, I don't know, aggregates latitude and longitude and assigns that to a district ID or whatever. So in this grouping key function, the vertices and the edges are grouped by. And in addition to these groupings, when we have the summarized version now of our graph, we can apply aggregate functions. This means we can just, I don't know, counting the vertices or edges that are grouped together, or calculating like a minimum, maximum, or average of a property value. And the grouping result, again, is a graph stream. So in real time, we have our grouped results as an output. And the applications for this graph stream grouping can be, there are many applications. So you can use it as a pre-processing. For example, if you have like an online page rank calculation, you can use this graph stream grouping to first group on the city attribute of users, for example, if you have persons inside the graph stream. Or you can use it as a post-processing. So after an applied pattern matching or stream analysis, like a community algorithm, you can group then all people with the same cluster ID together. And for sure, it's good for understanding the graph stream in general, to explore it, which labels are affected, which properties are affected, how frequent different types arrive, and so on. And during this aggregation functions, we can also reveal like hidden information, like how an average value of a property changes over time. Yeah, but grouping this graph stream is not simple. So therefore, here at the Leipzig University, we developed a framework that can do or can handle property graph streams and can group them. And we call this the graph stream zoomer, because you can group the graph on different granularities. That means like zooming in the graph stream and zooming out as you configure it. It's open source, available on GitHub, so you can just, I don't know, clone it and try it out. And it's based on Apache Flink. That means Apache Flink is the distributed stream processing engine, which means it's horizontal scalable. So, and here's an example how this graph stream zoomer works. So we have on top left an input stream of bike rentals between rental stations. That's our input stream. We have on the bottom left our grouping configurations. We say a window of 10 minutes. We want to group the vertices and edges just by their label. And we want to add a counter aggregation on the vertices and edges. On the right side, you see the result. So for every 10-minute window, we get this grouped graph as a result, where we group by label. So we have just station labels here in the stream and just a self loop of a trip with the according counts. But it doesn't have to be that simple. So we can also define like a more complex grouping configuration, like this one. Here, we want to group like the vertices on the district. It's a user-defined function that uses latitude and longitude to map it to a district ID of the city. The edges, we want to not just group on the edge label, but also on the user type property of the edge. And for the vertices, we want to calculate like the average latitude and average longitude for visualization purposes, for example. And for the edges, we also want to aggregate the minimum, maximum, and average duration of the bike rentals. And the result is here on the right side. So for every 10-minute window, we get this grouped result where we have the aggregated stations and two kinds of trips, one for subscriber user type, one for customer user type, with the according aggregation functions here. So the aggregation function leads to new properties in the resulting graph. Okay, this is how you can configure our operator. So it's written in Java. That means you kind of write the grouping configuration here in a Java API that we created. You can define the window size that you want to use. You can define which the vertices should be grouped on, which the edges should be grouped on, which vertex and edge aggregation functions you want to use. And then at the end, you can apply this operator on a graph stream, which is like an implementation of the graph stream data model, also in the graph stream zoomer. So this is how you call the operator. And now Kevin tells you how we can use now this grouping to get information from the CDC stream.
Yes, thank you very much. All right. So in the introduction, I told you that I worked with a lot of customers that basically have the same problem, or at least a lot of them had the same problem. And it was always around the question is, what is actually happening in your graph? Do you know what happens in your graph, what happens in your database on a day-to-day basis, maybe? And actually, most of them didn't know. So I'm talking about subjects like, how does your graph evolve? How does it change, right? Something like this. And this is something that we can do now. Now we have the CDC, a powerful implementation in the Neo4j database. Now we are able to stream all this information out, and now we use external tools, maybe something we implemented with the graph stream zoomer to analyze it. And this is exactly those two scenarios here. The left one is continuous analytics. That means based on the changes in your database, you are able to analyze and explore the graph evolution over time, right? So you can see how many create, update, delete operations happened, maybe on relationships. Yeah. So as you can see here in this example, relationships in this scenario, it's the trip label. We see how many was created, how many was updated and deleted, but also, of course, on nodes, also on node information, we can see this kind of information. What type of node was created, what type of node was deleted, and so on and so on. So it gives you a really good understanding how your graph evolves, right? And this is only the beginning. This is just like the first shot of implementation, something like this. But I think it can provide customers and users very insightful information about what is actually happening in their data. And the second scenario is the right side, is continuous aggregation. So not only the meta information about create, update, delete is there to analyze, but also average information based on attributes that we have on our graph, on our nodes, or on our relationships. Here in this scenario, we have this min duration, max execution, average duration, but imagine you have something else. Imagine you have something like a warehouse with items and so on. And you want, over the course of a day, you want to see the average information of how many items do I still have left in my warehouse? What do I expect to come in the next few hours or in the next few days? And you get basically an instant idea of what is available and whatnot. So we have those two different use cases basically currently overlapped, right? So meta information about the evolution and also some payload information that we can aggregate in our stream. So there's a lot of potential, as you can see, using the CDC feature, which I find very exciting, and I love it, to be honest, right? It's a really nice feature. All right, then I think we can switch now to demo time. We are perfect in time, I think. And for the demo, I quickly want to introduce you the architecture, how it's currently used. So we have the bike rentals, and I think you might know the data of that. It's the New York City bike data. We load this in an iterative fashion, in a periodic fashion into Neo4j to create CDC information, right? Change Data Capture. Then we have the CDC Kafka connector I already told you about. Kafka as our stream platform. Then we have the Flink Kafka source. So Flink is connected to Kafka, listening to the topics. Then our algorithm is in place where the magic happens, and then we push this information into our TCP socket. And then we have Wi-Fi, a very nice platform from YWorks available as an front end. Okay, Christopher, take it away.
Okay, so I will take now here and show you our demo. So I will first start here on the top left, the script that is loading edges into the Neo4j database. And we have started here. We can have a look into our Kafka topic, where we see that here are the CDC messages coming in into the Kafka topics. So what we have here are like, we have the information that Kevin shows us. So we have the full CDC mode. We have there's a relationship created. It's from type trip, and it has several. It's between two stations, and it has several properties. And this information from the topic we consume by the GraphStream Zoomer. The GraphStream Zoomer runs in an Apache Flink streaming job. So this is the user interface of Apache Flink. So we see here we have many transformations where this CDC data flows through. And at the end, as we saw in the architecture, it's pushed to a TCP socket, and then it's consumed by a WIFI files front end. And here, since we know the latitude and longitude of the stations, we have here New York City with all of the bike sharing stations, and we visualize here in a 30 seconds window all the create relationships that happened in this 30 seconds window grouped by our zoomer. So let's see, let's look for a create vertex, create edge here. And if we hover, we see we have like a count of 2. That means like here we are 2 edges summarized, and we have minimum, maximum, average duration in minutes for this specific edge. Yeah, and here you see like every 30 seconds when the new window was emitted, we get like the new information. Right? See here this big edge. So the count is on the edge width here. We see here are 7 trips aggregated, and we see with a maximum duration of 7 minutes and average duration of 5 minutes. So it's like an more or less an interactive interface where every 30 seconds it get like updated the results of our GraphStream Zoomer here in this visualization. It's just for this small demo to kind of show you what can be done. And in this example, we just have the create because our script just inserts edges. If we had a script that, I don't know, just also updates the graph or deletes stuff, then we would also see here like delete events or update events, and we could like also aggregate the properties that are inside this. And with that, we are done. So let me go back to the slides, to our last slides. I think since I have the word now, I will just close the session. So thank you very much for listening. Special thanks goes also to Sebastian Müller from YWorks, because he prototyped us this demo at the end with visualizing it on the map. And also a student of mine, Max Zimmer, because he helped really by contributing to this GraphStream Zoomer. Yeah, so feel free to reach out, also ask by mail or now here in the Q&A section. So thank you very much.